Good morning, everyone. This is the third tutorial for machine learning for constitutive law. In this tutorial, we will talk about geometric learning that actually apply for training a hyperelastic energy functional. In this lecture, our PhD student from Colombia, Ming Xiao, is a programmer, and then we're going to use PyTorch to create an elasticity model that actually take graph data as an input and output the energy functional that if you take derivative of it, you will get second particle stress. Okay. And you can find the informations from the paper that lists here, the geometric learning for computational mechanics part 1. And the link is actually also provided in the Jupyter notebook for the short course. Notice that in the paper that we present here, we actually are implementing the geometric learning using a TensorFlow, where in this tutorial is using PyTorch. But the performance is very similar, and we actually have a very similar design in between this paper and this tutorial. Okay, so I will go through the details. So this lecture contains 6 parts. The first part is the installations of the Torch geometric package that actually basically provide the convolutional neural network to learn the encode feature vector for the graph. We will talk about how to prepare the data, scaling the data, load the data, and again run the sublab training for the data. Now, in the previous 2 lecture, the machine learning is a pure supervised machine learning task, but here we will do something a little bit different. We would have a semi-supervised learning setup, very similar to the classical semi-supervised classifications with graph convolutional neural network by Keith in 2017, but instead we were actually trying to using it to change energy functional. Okay, and we were going to show some of the text results. For those have the registered for the course, by now you should have access to the source code and the training data. So here we will just provide a walkthrough. Let me show again. We would actually run the entire code in the collaboratory. So you just click connect, and then you can see the rank and the desks are actually allocated. And then you can actually run the code from here. In this case, the training actually take a longer time, so I already run the entire simulations. But you can also actually also try it when we actually run the test. But the major difference between the previous lecture or the previous tutorial and this tutorial is that in here our goal is not just to change energy functional for a particular microstructure, but for a family of RVE. So as we can see from here, there is a 2 branch to actually construct the learning algorithm. The first part is actually the geometric learning encoder. So this is actually in here, we use a polycrystal data as the input. And then the polycrystal actually contain local feature for each individual grain, and together they assemble together. And that will actually provide us to an opportunity to represent the connectivity as a graph, and the node feature actually are encoded in the feature matrix. The important thing about this is that these 2 inputs are actually going to put into the geometric learning encoder to actually create an encode feature vector. So you can think about it, this is some kind of data that are getting embedded into a vector space that are of lower dimensions, and from that, the feature vector also function as a descriptor of the original microstructure. Now, this is the unsupervised learning branch. We're calling that this whole method is a semi-supervised. So that also have a supervised learning branch on the other part, which take a deformations tensor, in this case, the right Cauchy-Green tensor, as the input and output as scalar, energy functional, and we reuse Sobolev training again, which meaning that if the derivative of it would give us the second empirical stress. Okay, so here we will just provide the specific input for the torus geometric. You should be able to run the code without any problem. So let me do the test here. Okay, and then you can actually see the versions of the code that you're using. So and if you have a better machines or you actually have more resource, you can simply change those setup for the particular computer you have. Again, you can actually connect to a local machines in Jupyter. Now, if assuming that if this is successful, you should, and then you run it again, you should see this. So that indicating that the package are actually installed properly. So to make it convenient and making sure that the tutorial can go really uneventful, I will just install the torch geometric from scratch here. Now the next step is to prepare the graph database. This is actually to deal with a particular situations. In this case, a polycrystal. A polycrystal is a type of material that are assembled by, of course, individual crystal that are actually put together. In this case, we were assuming that the crystal is completely, the polycrystal is completely packed. There is no small hole in it, although in principle, that we can also try to implement the hole here. Now, the important thing is that typically the semi-supervised learning can be done by using a convolutional neural network. In fact, our colleagues from Sandia, actually from the Sandia Livermore, Dr. Rhys Jones has also previously done some work on that unsupervised learning on the convolutional neural network. Here, the only thing that different is that before we actually apply the convolutional neural network on the image, we would actually processing it and then actually have a lower dimension graph to represent the original image. And then we actually would train another encode feature vector that are even lower dimensions from the graph so that it actually become a descriptor. So this is actually the crystal, and then here we will assume individual grain as the nodes, and then if they're connected, we will add an edge to it, and we would actually create a node weight graph, which means that all the nodes, the size of the particle, the shape of the particle, the orientations of the material, all those features are put into the feature matrix, and the graph connectivity are actually represented by the adjacency matrix and also the degree matrix, and ultimately the graph Laplacian. So this is actually essentially become a matrix that will present two matrix that will present the microstructure. The L symmetric, which is actually the symmetric dice graph Laplacian, is represent the connectivity. And X matrix, the feature matrix, is actually containing the independent particle behavior or feature or attribute. One thing that is important to remember is that this is actually not the only choice to represent the data. For example, we can obtain another matrix in which the edge is actually represented as the nodes and the particle that connect that actually share the edge could be used as on the other hand, could be an edge. Or we can represent the same data structure in a hierarchical way, in which case we will generate a direct graph where individual point, edge, and surface and volume can be actually represented in also in a graph manner. There's no single choice that that could be dominant here unless we tried it. But one of the intuitive way to do it is just do it in the way that we show in this figure. Now, there are also another small thing that are new from this tutorial that doesn't happen in the previous tutorial 3A and 3B, and that is that we actually need to mount the drive, our Google Drive, to actually load the database. So in this case, we don't generate a database from analytical solutions. We generate the data from the FFT simulations. So I think it's too time consuming to try to run the simulation live in a tutorial. So we already generate the data from the FFT. If you use those data for your previous research, by the way, please cite the paper at the beginning. And here, go back to this. A simple way to actually loading the data and still running on the cloud is basically just mount the drive. If I click on it, you would actually see authorizations code. And then actually, this is actually for security reasons. So if we click on this, you can actually log in with your computer. So here, I just use the Gmail account for the conference, and then you can copy the code and then you can actually put the authorization code here. Okay, so once it's authorized, yeah, you will see the mounted at Google Drive. Now, one thing that are actually important is that in order to use the database, you need to actually create a shortcut for the Google Drive. So if it works, and this is actually why we put the running there, you should actually see what the folder that are here, the graph, the elasticity folder, and then the graph process folder, and then also the geolearn.py that actually provides some of the details of the implementations. Okay, so here you can see that probably see a little bit more that is necessary, but then the key element is here. So how do we do it? Make sure that we did one thing that actually pretty trivial, but lots of time. If we are not familiar with cloud computing using the collaborative, we may forget. So you see these two folders here. If we click on it, you can see the microstructure informations here. And then you can also see the other database that provide the graph data. So let me go back to here. Okay, so in order to actually load the data properly, click on the folder, right click it, you will see a add shortcuts to drive. Make sure you add it to your drive, otherwise you would actually find that the collaborator cannot find your file. So add it to the locations where you run the Jupyter notebook. So add shortcut to drive, and then that should be fine. So in here, we use the data both from the elasticity folder, which compute the FFT results, and then the graph process actually generating the graph from the microstructure. I'll go back to the code. Okay, so we explained that we only have 150 RVE here. This is actually, again, in the smaller spectrum. I think for the graph, to learn the graph efficiently, you typically need more graph, need more microstructure. The reason is very simple. The goal of this learning is not to generate energy functional for a particular microstructure, but for family of microstructure. Basically, every graph that you put in there, you should be able to, the new network training, if it's successful, should be able to generate new energy functional. So what it means is that you need to have all the different, you need to, in order to extrapolate it properly, we need the we need the we need to actually sampling enough to have enough data distribute in the parametric space in order to predict it properly. So now, when do we know that we have enough data? I guess one thing we can actually check is to see if we're given a new microstructure, or that if you sample enough new microstructure that haven't seen by the computer, whether we can actually create energy functional that are actually reasonably accurate. Now, but here the Encoder feature vector is actually playing a big role here. Again, the interesting aspect is that you can actually design the dimensions of the Encoder feature vector, and then that would actually make a big difference on how much sample, or how do you represent the microstructure. Now, notice that this would still be the important thing is that because we are not directly controlled or actually manipulate any informations from the from the voxel image, the graph itself is actually already in a much smaller dimensions than the original microstructure that are actually stored in a voxel image. So we deal with a graph that are relatively small. Maybe much smaller than a social network, but a little bit larger than, say, a molecule structure, which we can find a lot of applications in the chemistry area, where the graph neural network are actually used to design or actually predict property of molecule. Now going back to that, I just want to go over the code. So we have 150 database, which is relatively small. And then the next thing is basically to load the data. Now this is actually pretty tedious, but also potentially be the difficult part. Luckily, Torch actually have with a decent auto differentiation function, so we basically can using the autograd to actually give us the derivative we need to complete the soft training. I want to explain a little bit about what we are doing here. So basically, we need to build two matrix for each image. The first one is the graph Laplacian, which actually can be obtained directly from the graph connectivity, and then basically to build a graph. This is actually the part of the code that actually build a graph, and not necessarily build a graph, but load the graph into the Torch database. And then the first part is actually the feature vector. So here we actually including the following feature for each nodes: the volume, the number of neighborhood, the area, the dimensions, and the sphericity, which is actually tell us how round it is, and then a number, the phase angle, the number of phase, and then the orientations represented by the Euler angle. So the interesting thing is that you can actually put other attribute to it, and then you may actually get a different feature vector. And this is something that is actually not immediately clear what information should be put into the feature, and that would actually also affect the training. Now, one thing to remember is that if you read the paper, you'll find out that this is actually for studying a family of polycrystal that are sent by a different FCC. They have the same Young's modulus, but because the FCC grant is anisotropic, we need Euler angle. In general, if you actually have a sample of heterogeneous material, let's say a soft inclusions in a hard matrix, or actually have one hard grain and soft grain mixing together, then we actually could put also Young's modulus or any elasticity model into the feature. But one thing that is important is that in this design, all the nodes are actually have the same number of attributes and the same type of attribute. They don't necessarily have the same type values of the attribute, but then the set has to be identical. So if you actually try to build a model, feel free to change this part. And basically, this would be enough to generate the feature vector, and then load it into the torch learning. Okay. The graph Laplacian, the calculation of it, we will talk about it in the main lecture, but you can see that basically all of this is coming from the graph connectivity and then adjacency matrix that actually indicate which particle is actually connected to which particle. Then we actually need to prepare another branch of the learning. Remember that this is actually a semi-supervised learning that have an unsupervised component, but also have a supervised component. Another data set we need to prepare is actually the supervised learning, which gives us the questions and the answer of some labeled pair-based data. In this case, the input is the right Cauchy green tensor, which is actually FTF or actually UTU, which actually is a second order tensor that I actually represent with index in the reference basis and the corresponding stress measure is a second polycrystal stress, which could be obtained from the first polycrystal stress as well. So this is actually the pair. The interesting thing is that you may not even need the energy as a label to train your energy functional, because knowing that or you can make an assumption that a stress-free configurations have also no string. In this case, you have a point that are actually for C equals to I, then the energy equals to 0. And then you can simply use the gradient to reconstruct the energy functional. In that case, that would be S. Okay, so that would be a possibility. Also, the C is not the only choice to represent the to actually train energy functional. A lot of time we would also like to use the E matrix, which E tensor, which has a nice property. When E equals to 0, the energy and the stress also go to 0. Where if you use the C or you use the left Cauchy green tensor B, then the energy should go to 0 when the string measure is actually identity tensor instead of 0. Anyway, so this is a matter of choice. Provided you make the right choice, the solution should be very simple. I won't repeat it here. This is very similar to the previous PY Torch tutorial. Basically, we just need to use the library to actually converge the column vector into a matrix, and then or tensor, and then in that case we can actually simply using the nice feature of transport, and then the inverse to actually obtain the stress and strain measure we want. So if you have a background in container mechanics, it's actually pretty yeah, it's pretty obvious. So I'll just stop here. The next part is actually on the rescaling. So again, this could be just for convenience purpose, and it also help the loss functions to be well balanced. Again, if we have machine learning problem that have more than one objective, we want to minimize the discrepancy of the energy, but we also want to minimize the discrepancy of the stress as well. So one way to actually make both objective roughly saying being more or less equally important is actually just rescaling everything to the energy term to 0 and 1, and then the stress term to 0 and 1, so that roughly the first objective and second objective relatively have a similar range of a behavior. And then we construct the data loader. I won't go over the details of it, but basically it's just to put everything back into X and Y coordinate, and then basically load all the data there. Now the next part is actually the launching the hybrid H1 training. Now here this is actually really simple, because in the PyTorch in the torch geometrics, surprisingly most of the stuff are already there. So we simply need to use that mix GNN. If you click on it, you can actually see the details. Okay, and this is actually from the geometric learning parameter, and then and you can actually see the setup of the neural network. Now the output is 9, and then the input actually have 9 components, but actually only 6 is actually necessary, because this is actually because the C tensor is actually symmetric, and then the 8 output 1 would be, the reason is being that the output is the energy itself. Okay, and then so this is actually the setup of the graph neural network. And let's see. And we have the optimizer setup, and then you have a schedule, and then the whole machine learning training, and because it also have a predefined H1 scale hybrid that are actually coming from the code that we written, and then we put it into the folder, so we just omit it here. Okay, so if we put it together, so this is all set. I won't go over the training here, simply because it probably will take 40 minutes in a typical computer, but you can see the lossing function going down. Now, one thing that should be noticed is that this is a much harder training, because it actually the task of the neural network is actually more general. Okay, so it's not trying to train energy for a specific RVE, but if you change the particle itself, you should be able to use the same neural network to automatically get a new energy functional, which if success, it will be very nice. Now, one thing that I would like the audience to also think about, and this could be a nice project, is that when we represent a graph, you would actually need to put an order or tag on it. Okay, so for example, we will call this particle 1, this 2, this 3, and 4. Now, if I change the tag or the order of the representations of the nodes, I would basically change I would actually basically change the the look of the graph Laplacian, the adjacency matrix would also be changed. The important key here is that no matter how I change those nodes, they are the name tag that we are given are actually completely artificial. So even though it changed the graph Laplacian, it shouldn't change the energy functional that we obtain. And this is something that I would like you to try if I actually change the name or the order of the nodes. So what would happen? Now go back to the main story. You see the training go down. The training is a little bit slow than what we previously, but you can see that the order does improve quite a lot after approximately 35 minutes. Okay, the training, the test and everything is actually very simple. And so I won't repeat it here. Basically, again, we actually have a one throw test. We actually, out of the 150 data, a small portion of it are actually not included in the training, and we're using it for validation purpose. So this is actually some of the stress string response. As you can see here, compared to the previous training, the training is getting harder, and then the match is actually less impressive. But then this is also the test result is actually on a new microstructure. Whereas in the previous task, we are actually predicting a new loading path for the same microstructure, and hence the difficulty is actually different. So if you like, you can actually also try to increase the database to see whether it improves. But also another thing we haven't actually discussed, but could be very important, is the equivariance property. If I rotate the entire particle to microstructure, I may actually get a different constitutive response if I loading it in the same reference frame due to the anisotropy of the material, but I should obey material frame indifference. So in this training, would I able to have that? The answer is that if you just do it like what we did here, probably not. We need some special treatment, either by putting it into the loss functions. Well, one way to do it is to rotating the data itself and then conduct an additional training. Another way that I actually have a lot of improvement recently from the geometric learning community and also in the convolutional neural network is to introduce the equivariance, so that when the image is rotated, the physical property can actually, or the predict quality should actually get the same number of adjustment accordingly. Okay. So this is actually the end of this tutorial. The next tutorial would be about reinforcement learning. I hope you enjoy this lecture, this tutorial. I think that I would like to say that you probably need to go over the lecture to understand the theory behind that. But feel free to take a look at the code, and then more detailed explanation are actually in the paper. I think the paper is actually very simple, and I think that should be able to. I think you should able to read it without any problem. So let us know if you have any questions. I hope you enjoyed this tutorial, and thank you.